Hello, students. In this video, we will discuss the effects of intermolecular forces and how their varying strengths can influence the physical properties that we observe. So the effects of intermolecular forces. Basically, without intermolecular forces, nothing would exist but the gas phase. Why? None of the molecules or atoms we see would stick together. They would be all far apart, moving at fast speeds, resulting in all gas phases. But we know that there are intermolecular forces, and we do see the condensed phases of both liquids and solids. And now we're going to look at the effects of intermolecular forces on different properties. So we'll discuss solubility and miscibility, viscosity, capillary action, surface tension, evaporation, which leads to vapor pressure. There's always, over any liquid, there's going to be an evaporation at any temperature, and as things vaporize, they exert vapor pressure. And then boiling point and melting point. So one of the things you want to remember is the term like dissolves like. This is used a lot in biology courses, but basically what it means is to dissolve in a solvent, the solute has to have similar polarity. So polar liquids are miscible with other polar liquids. Miscible means when a liquid dissolves in a liquid. Soluble means when a solid or a gas dissolves in liquid. So a lot of times students mix, they confuse and just say solubility always. But when you're talking about a liquid going into a liquid, we use the term miscible. To dissolve, let's say in water, which is polar, the liquid must also be polar. If it is non-polar, it will not be miscible. So miscible means mixing without seeing two phases. So immiscible liquids would be a heterogeneous mixture. Miscible liquids would be homogeneous. So in all three of these examples, you see immiscible liquids because you see two phases. You can see something floating on top. So here you got oil because an oil tanker spilled some oil on water. That's why sometimes these can catch on fire even on bodies of water. Here we have vinegar and oil probably, and here we have pentane and water. And what we see are they're not mixing together, okay? So there are two separate layers, they're immiscible. So again, why is that? Well, we learned that pentane, the alkane, has all carbon-hydrogen single bonds, and because it's symmetrical, it's a non-polar molecule. We know that water is polar. So as a result, they don't mix. Why? Like dissolves like. So if you added pentane to water, it would be an immiscible liquid. The attractive forces between the water molecules are stronger than for the pentane. Why? Because water can hydrogen bond to itself. Pentane, which is nonpolar, can only London dispersion. So the pentane molecules stick with what they're used to, and the hydrogen bond sticks to what they're used to. And we get two immiscible liquids and a heterogeneous mixture. So just remember, like dissolves like. Now, we also know that if I have a polar molecule, it will dissolve in water. Well, we know that water can hydrogen bond, and so can ethanol. Why? Because ethanol has this OH group, and we see that oxygen is bound to a hydrogen, which creates the superdipole that allows for hydrogen bonding. That's why you have mixed drinks. I mean, you're not drinking pure ethanol. It has to have the solvent water in it. I guess that's a good thing. When we talk about salts dissolving in water, right? That's soluble. And that again forms those ion dipoles that we talked about in an earlier video, where you have the negatively charged anion surrounded by the positively charged hydrogens, and the cations are surrounded by the partially negative oxygens in water. So you can think of this as, super, an ion is a super, super, super dipole. There's such a difference in electronegativity. There's not an unequal sharing of electrons, there's a complete transfer. So of course, It's going to dissolve in water. So now that we talked about basically solubility and miscibility dependent on intermolecular forces, and again, like dissolves like, we can also see that even when we have pure substances in liquid form, their intermolecular forces can affect certain things such as viscosity. So viscosity is the resistance of a liquid to flow. So if I have stronger intermolecular forces, the liquid is not going to want to slip and slide. There's not going to be as much freedom of motion because the intermolecular forces are really strong and they stick to each other. So there's not as much freedom of motion. If there's not as much freedom of motion, it's a more viscous liquid. So I know you thought of what I thought of, pancakes, right? So syrup is very viscous. It has really strong intermolecular forces because there's large molar masses in maple syrup molecules. So viscosity is the result of intermolecular forces. The stronger the intermolecular force, the more viscous the liquid. An example of a non-viscous liquid would be gasoline. If you've ever poured gasoline on a hot day into your car and a few drops fall on the asphalt and then it quickly vaporizes, well, that's because it does not have strong intermolecular forces and it's not very viscous, and it also is volatile and evaporates very quickly. So now that we talked about flow, let's talk a little bit about an upward flow of a liquid in a thin tube. So that is called capillary action. So that's basically where water can flow up against gravity. Now, where do we see capillary action? Plants. When you talk about the xylem and the phloem, you're talking about the vascular tissues of plants, and essentially they're narrow tubes with carbohydrates such as starch. So the narrower the tube, the higher the liquid can rise. So you have a greater capillary action with a narrow tube. But capillary action, the ability for the liquid to flow against gravity, is also influenced by intermolecular forces. So there are two forces working. There's cohesive and adhesive. So let's describe those. Cohesive forces are the attraction between the molecules in a liquid. So cohesive is the intermolecular forces with the liquid with itself. Adhesive forces are the attraction between the molecules and the tube. So those are the intermolecular forces between the liquid and the tube. So if we go back to plants, right, and we talk about their vascular tissues and bundles, they're made of carbohydrates, right, starches, cellulose, and they have alcohol groups attached. So water has basically OH. It's attracted to the OHs and the alcohols and carbohydrates. So through hydrogen bonding, there's an adhesive force, and it will rise up the tube in the vascular tissue of plants, and that's what we call capillary action. That's why trees, which are huge, 20 feet, still get water at the very tips. Now, we actually see this capillary action in lab, and we'll see again that the cohesive forces are going to pull the interior or the bulk of the liquid upward, and the adhesive forces are going to pull the liquid up the side of the container and help it climb up. So the liquid rises up the tube until the force of gravity is too strong. Once that occurs, it can't be pulled up any higher. So again, the narrower the tube, the diameter, the easier it is for it to climb up because the adhesive forces are closer in proximity and that intermolecular force is stronger. Believe it or not, this capillary action affects the shape of the surface and the meniscus. So when we're reading volumetric measurements and we're looking at the meniscus, we have mostly been looking at the curvature of water, okay? So we've been saying, look at the bottom of the meniscus. But what explains when we look at, let's say, liquid mercury, like in a barometer, where it has a different shape. Well, why does it have a different shape? It goes to the battle between adhesive and cohesive forces, which is, am I more attracted to the liquid or am I attracted to the surface of the container? So adhesive versus cohesive. So the meniscus of water is concave, so you can think of this as caving in, and its adhesion to the glass is actually stronger than to the cohesion of itself. So that's why it's kind of sticking on the edges, but it can't pull the bulk up anymore. The meniscus of mercury is convex. So convex, it's in a different shape. And that's because it's actually more attracted to itself. And that's because metallic bonding is extremely strong. That's why metals have such high boiling points. So now that we talked about the meniscus and reading the surface of the meniscus, looking at its shape, let's talk about what happens at surface of liquids and surface tension. I call it surface tension is basically the attractive force pulling the surface molecules into the bulk of the liquid. So at the surface, there's not as many neighbors as if you're in the bulk of the liquid. So the surface molecules, as a result, have less intermolecular forces and attractives or attraction because it's only got neighbors to the side and below it. So it doesn't have, it's not as stable, it has a higher potential energy, and it wants to have a lower potential energy. So to lower its potential energy, the attraction to the bulk pulls the surface molecules inward, minimizing surface area. And we can see that here. So again, if I'm looking at the bulk liquids, it's got molecules all around it. So it has all these attractive forces all around it by neighbors. So it lowers its potential energy because it's more stable because of the increase in electrostatic attractions. Again, at the surface, there's no liquids above it. So everything's being pulled downward, and that creates the tension. So it's kind of a skin at the surface of a liquid that resists penetration because everything's being pulled downward. It's hard to penetrate there. So does that mean more dense objects can float? Now we know that that's not true. If I throw a penny in a cup of water, it's going to sink because the penny is a solid, it's more dense. But sometimes, if you're very careful and the more dense object has a large surface area, you can see it float. Like a really common, K through 12 lab is get a Petri dish, add water to it, and carefully place a paper clip, which is made of metal, which is more dense, but it will float due to its large surface area and that downward pull on the surface. Since we're talking about the surface, let's talk about evaporation, because evaporation occurs at all temperatures. And essentially what evaporation is the liquid escaping the surface. So what do I mean by escaping the surface? Well, we have to realize when I have a liquid, the intermolecular forces are keeping it in that condensed phase. However, if I have enough kinetic energy, so if there are hot, fast moving water molecules at the surface, they can overcome that downward pull that we just talked about and escape into the vapor phase. And essentially what I call that is that requirement is an escape velocity. Okay. To reach that escape velocity, you need to be moving fast and you have to be at the surface to overcome that downward pull. The ones in the middle, they can't escape, even if they're moving fast enough, because there's too many molecules in the way. So the larger the surface area, the faster the rate of evaporation. So if you ever have a puddle, right, in your backyard, let's say on your driveway, well, what's a really easy way to have that puddle evaporate and dry up quickly? Get a push broom and sweep it across the driveway. And by doing that, what do? You increase the surface area so you have a greater probability of molecules at the surface and escaping. Now, when they do escape, right, it allows them to become a vapor, right? So essentially, when something is escaping or evaporating, they're a vapor. A vapor meaning they're a gas. The process of molecules of a liquid breaking free from the surface is called evaporation, and you're making vapors. So how does this happen at any temperature, right? So if we go back to our understanding of kinetic energy, and we know that kinetic energy is proportional to temperature or thermal energy, and we can think of that really when we talk about the kinetic energy of a system, we're looking at averages, right? So not all molecules have the same amount of kinetic energy, even at the same temperature. So we see the distribution, right, of thermal energy. How? We look at the kinetic energy, the movement of the molecules, the speed. So it's increasing in kinetic energy as I go left to right on this graph, and the fraction of the molecules that have that particular kinetic energy. And like most normal distributions, there's a distribution. There's always some majority average, but there's always some molecules that are going to be moving faster and some that are going to be moving slower. So when we say average kinetic energy, that's what we mean, but there's still some that are moving faster. Now, there's always a minimum amount of kinetic energy to escape. Remember, I called that escape velocity. So there is a minimum amount of energy to reach that escape velocity. So only a small fraction of the molecules in a liquid have that kinetic energy to escape, right? And not only is there a small fraction that has that kinetic energy because they're at the tail, they have to be at the surface. But what we do notice is as temperature increases, the fraction of the molecules to escape increases because the overall kinetic energy increases. So it's shown in this graph that the lower temperature in blue has an average kinetic energy like this, and some of the molecules can escape. Once I heat this up, that average, or I could think of it as that normal distribution, is shifted to the right. And now I see at the higher temperatures, the new distribution of kinetic energy, and now more molecules have that escape velocity that I discussed. So what does that mean? Well, more molecules have the escape energy required to overcome the intermolecular forces and vaporize at higher temperatures. There's a faster rate of evaporation. But again, realize that those also have to be at the surface. So the gaseous form is called a vapor, and this leads when things are evaporating above a liquid, right? Gases do what? They exert pressure. So above any liquid, there's a vapor pressure. Why? Because there's evaporation. Now, yes, above any liquid, there's evaporation, which we're going to call vapor, but realize that some of those vapors may actually collide, right? So if I have a liquid, let's say I have a body of water and I have vapor, some of those vapors will collide with the surface of the liquid. Now, if some of those vapors are moving slow, they'll get recaptured back into the liquid that they collide into because they're transferring some of that kinetic energy to the liquids that they hit. So now they move slower and they condense. And we see this if you've ever, put a cold soda out and there's a good amount of humidity. What happens on the outside of that cold can? We get condensation. It's what happens at, night. And when we wake up in the morning, there's dew or fog. It's cold. So the vapors are moving slower and they're condensing and forming dew and liquid. So some of those vapors that collide into that surface will stick and form droplets. And we call this condensation. So realize there's kind of this battle between evaporation and condensation. Now, if I have an open system, as things vaporize, they'll just escape because they're vapor and they're moving quick and you can't recapture them because they're vaporizing and escaping. But if I take a closed system, so I take water, I put it in an Erlenmeyer flask, but I trap the vapor by capping it, what's going to happen is eventually this liquid is going to evaporate. And shortly after it evaporates, I get vapor above this liquid. Now, over time, right, initially, the rate of evaporation is faster than when these molecules recollide and condense. But over time, there's only going to be so much room for the vapor above this liquid if I cap it. So eventually, the condensation and evaporation rates will occur at the same speed. Okay? Doesn't mean I have the same amount of vapor as I do liquid, because again, the vapor takes up more volume because there's more space, but the rate at which condensation or evaporation occurs is the same. That's referred to as equilibrium, equal rates of evaporation and condensation. But there is a requirement. I have to have a closed system. So it's called dynamic equilibrium because it happens dynamically. And once those rates are equal, the total amount of vapor and liquid will not change. So for every, if I go back, for every vapor that recondenses, it's got to push something out and one water molecule will evaporate and vaporize. So it becomes an equal rate. So evaporation and condensation are still occurring, but they're at opposite directions. So there's no net gain or loss of vapor or liquid at a dynamic equilibrium. But what we really want to focus on is, because you will study equilibrium in greater detail in other courses, what we want to focus on is the energetics of vaporization. So when the high energy molecules are lost from liquid, right? So if the faster moving molecules are lost, that means the overall average kinetic energy goes down, right? Because if I'm losing the fastest molecules, then the average is slightly shifted. So the energy, if it's not drawn back in, the temperature will decrease. Now, why am I bringing this up? This explains why we sweat and perspire, right? So if you sweat, you have a liquid. Well, as that liquid vaporizes, the remaining sweat on your skin is colder because the faster moving particles escaped. And that's good because that keeps you cool. Vaporization requires input of energy, right? So for something to evaporate, right, I need to put in energy, right, to overcome those attractive forces that pull downward. Well, I was talking about sweat. Where does that energy come from? Well, our body's hot. It emits heat and it causes the sweat to evaporate. Now, why am I bringing up vaporization? Well, we need to understand that when things vaporize, again, there is a pressure exerted above the liquid, and that's vapor pressure. Remember Dalton's law of partial pressures, where we can account for the pressure of the water vapor when collecting gases by water displacement, right? So we talked about the dry gas and the water vapor equal the total pressure. Well, that's part of the vapor pressure that we talked about. What you have to understand is the weaker the attractive force, the easier it is for the liquid to vaporize. Okay, because if the liquid isn't sticking, it's going to escape and overcome those intermolecular forces a lot easier. So the weaker the attractive force or the intermolecular force, the higher the vapor pressure for the liquid. Higher vapor pressure typically was referred to as a more volatile liquid. And that was the example that I used earlier. When gas hits the asphalt on a hot day, it evaporates really quickly. Why? Well, gas is an alkane. Alkanes are nonpolar. Nonpolar means it can only have London dispersion forces, which is the weakest intermolecular force. So it's easier to overcome and vaporize. Now, what about vapor pressure versus temperature? We just said if I increase the temperature, things evaporate more quickly because I reach that escape velocity. Well, if I'm increasing the temperature and things can escape, that means I'm going to have more vapor. So as the temperature increases, so does vapor pressure. Small changes in temperature actually make not linear changes, but exponential changes in vapor pressure. So the rate of growth depends on the strength of the intermolecular forces. One of the things you're going to be required to do is read vapor pressure curves. So with vapor pressure curves, you have the vapor pressure here and you have the temperature here. And one of the things I want to show you is they always show 760 torr or millimeters of mercury, because remember, that's equal to the standard of 1 atmosphere of pressure. And what we see is when water, okay, so here's the water vapor pressure curve, at 1 atmosphere, it requires 100 degrees Celsius to completely vaporize, right? At lower temperatures, you still have some vaporization, but you don't have a complete 1 atmosphere. So what does that mean? The normal boiling point for water is 100 degrees Celsius, because that's at what temperature I'll get 1 atmosphere of vapor pressure. We also see in the curves that they're exponential. And we see, based on the intermolecular forces, that the curve reaching the normal boiling point is dependent on that. So here we have water, which again can hydrogen bond, and ethanol can hydrogen bond, but it can't hydrogen bond as much because I've drawn this before. It can only hydrogen bond 3 times versus the 4 in a water molecule. And then the diethyl ether, it's a lot easier to boil off and exert a vapor pressure of 1 atmosphere. You only need 34.6 degrees Celsius, right? It has a lower boiling point because diethyl ether is only polar. I'll draw it this way. It's only polar. So it can't hydrogen bond. So it has a much weaker intermolecular force, so it vaporizes much easier, and it's a lower temperature required to reach a vapor pressure of 1 atmosphere, which is actually what we call as the normal boiling point. But again, you can see on this curve at any given temperature, water is vaporizing. It's just not exerting a very big pressure, and it is exponential. So as we increase more and more temperature, it eventually reaches that 1 atmospheric pressure. So boiling point, when we say boiling point, we're pretty much saying the temperature where the vapor pressure of the liquid is equal to 1 atmosphere. And now we call that boiling point. So if we're dealing with lower external pressure, so normally we say, the average pressure of a room is 1 atmosphere. But if we have less pressure, the boiling point is actually lower. And we see this. So at sea level, roughly, we see that atmospheric pressure is 1 atmosphere, so it requires 100 degrees Celsius to boil water. But if I go to the Mile High Stadium, the vapor pressure or the atmospheric pressure is lower, so it only takes 94 degrees Celsius to boil. If I go all the way to the highest peak on Earth, the atmospheric pressure is very low, so it's really easy to boil water. Well, why is that? When we think of atmospheric pressure, let's say we're on a mountain, right? If I'm down here at sea level, right? Think of gravity. I have gas particles, right? But gas particles are being pulled where? Due to gravity. Down at sea level, there's way more gas particles, so there's a greater external pressure. So if I have a liquid and these gas particles are pushing down on that liquid, it's harder for the liquid to vaporize and escape because there's a vapor pressure, an external pressure of the atmosphere pushing down on it. Well, at a higher elevation, right, if I'm trying to boil water, there's less external pressure pushing down on the liquid. Well, now the water can escape easier and vaporize. And that's why at higher elevations with lower pressure, I don't have to, you know, I don't require as much energy for the water to boil. So when we think of boiling point, really we're looking at when does the liquid reach, right? When does it reach a vapor pressure that's the same as the external pressure of its environment? Because at that point, right, the vapor pressure above this liquid is trying to keep the liquid in place. But as this starts heating up, now the liquid, it's not even at the surface, it's moving all over the place to overcome, it's gaining this kinetic energy and it's pushing back the bulk liquid water. And when it's pushing it back, now it can push back and escape and boil off anywhere in the liquid. It doesn't have to be at the surface. So that's what your boiling point is. So that's what we call boiling. And it's the temperature at which the vapor pressure equals the external pressure of the boiling point. So when we say water boils at 100 degrees Celsius, that's because we use the standard pressure of 1 atmosphere. So what do we mean by melting? So we've been talking about evaporating and boiling. What do I mean by melting? Well, as a solid is heated, we learned degrees of freedom or freedom of motion. Solids basically vibrate, right? But as I heat it, the molecules are going to vibrate more vigorously. And eventually, there's going to be a point where they have enough kinetic energy where they overcome the intermolecular forces that keep them in their fixed shape. And now they're going to start having a little more freedom of motion and more kinetic energy where they overcome that fixed lattice structure and they can begin to slip and slide and have that translational and rotational degree of freedom or motion where they begin to melt and become a liquid. And the opposite of melting is freezing. So the energetics of melting, when high energy molecules are lost from the solid, again, it's going to lower the average kinetic energy. So if energy is not drawn back into the solid, its temperature will decrease. I already talked about that with the evaporation. It's the same concept. So melting requires input of energy. Why? I have to overcome the attractive forces, provide more kinetic energy so that I can melt it and, and cause those freedom of motion. So melting is an endothermic process. Well, if going from a solid to a liquid in this direction is melting, right? And that's requires a positive energy. Well, going in the reverse, freezing, means I will lower my potential energy, and the result is lowering the potential energy causes a release in heat and is an exothermic process. So that's the phase changes. That's from the other video that I talked about. Again, going from a solid to a liquid, that would be melting. Going from a liquid to a gas, that would be boiling or vaporization. And to overcome the intermolecular forces, we need to put in heat. So all of these going in this direction are endothermic processes. People always get confused with the reverse. So just think the reverse, what's opposite of putting in heat? Lowering my potential energy level. So when things go from higher potential energy to lower, there's a transfer of energy. So I have to lose the heat, and that is an exothermic process. And what's the opposite of boiling? Well, we would say condensation. What's the opposite of melting? You might say freezing. So I hope this video helps you understand the effects of intermolecular forces on different physical properties and what those physical properties are. And to overcome the intermolecular forces requires energy. And the strength of the intermolecular force is going to determine the amount of energy that's required so that it can be overcome. So again, thanks for watching, and let me know if you have any questions.